Hi, today we're going to talk about AI breast cancer diagnosis for lesion segmentation. I'm James. I'd like to introduce my teammates Omkar, Yunjin, and Archil. So here we see a block diagram of our architecture. We have Unity for the chat window where the radiologist is at. We have the Rasa Chatbot server, Rasa Action server, running multiple of our Python scripts that are typically powered by TensorFlow and PyTorch. And Archil will introduce the topic.
The reason why we wanted to do medical imaging classification and segmentation is because 30% of cancer is missed in routine screenings. So we assist radiologists in diagnosing breast cancer through developing AI tools. Although state-of-the-art segmentation models do exist, improvements can be made to overcome their low performance. So we propose classification and segmentation methods by leveraging channel attention modules in our encoder-decoder networks for the precise segmentation of breast cancer regions using different models such as ResNet, attention Unet, LinkNet, etc. We'll start with our classification models. Next slide, please. So one of the tasks that we can perform using deep learning and convolutional neural networks is medical image classification that can serve as a tool to aid physicians. We train state-of-the-art models on 2D breast cancer dataset and evaluate them to distinguish the most accurate of the models. As illustrated in the table, ResNet 50 was the model that achieved not only the highest accuracy, but also highest recall score, which is a very important metric because we want to have as few false negatives as possible because false positives may be double checked, while false negative may lead to a delayed treatment of a patient. Now, Yunjin will talk about Unet model.
For image segmentation, I choose the attention Unet model. Here is workflow and diagram. Attention is a way of focusing on the relevant activation during its upsampling phase of Unet. This reduces the computation resource. Next slide, please.
So the main reason for using LinkNet was it utilizes the parameter really well compared to the other algorithms. So here we can see the layers of encoder and decoder. So encoders are used to extract features where here in the algorithm I'm using something called backbone, where backbone are like ResNet or VGG based algorithm, and they are used in the encoder. And then in decoder we use use pixel classification where we segment the tumor-based cells from here, and we can see that input image and the output image size are same. So with the help of upsampling and downsampling, it remains it helps us to it keeps the size same. And also here in the architecture, you might notice that I've used some extra layers of encoding and decoding compared to the original LinkNet model. So I've also used the library-based approach where I was not getting that accurate result, so I had to make some changes into it, and I added few more extra layers of encoder and decoder. Yeah, next slide.
Hi, everyone. So I also took a route of reading research papers and then found MSGRAP, multi-scale grid average pooling. It's similar to Unet, except that they utilize less connections between the encoding and decoding within the architecture. So here we can see a 2D image of MRI, for instance, gets passed into this network, and then multiple convolutions are being used to downsample the image, but then transposed convolution layers are used to upsample it to output a binary image segmentation. I've been working with the implementing of this architecture to support 2D and 3D image segmentation. And one of what H. Lee, one of the researchers from this research paper, found was using less connections resulted in better learning compared to Unet. It also resulted in overcoming noise often found in ultrasound, MRI, and PET imaging. I actually adapted this model to work with MRI imaging because originally it was working with ultrasound images. The other area I want to explore is working with PET imaging to analyze physiology area of breast cancer. And then the other part is group normalization is used instead of batch normalization to overcome generalization issues typically found with deeper neural network architectures, and especially in 3D imaging too. And then a larger grid size is used for obtaining attention-guided weights across the different pooling layers. Now we'll jump into the demo. We have a pre-recorded video for you guys. So here we have two different ways to run the application, either through Python scripts where we can run multiple parts of the app. And in this case, we have train PY that we're running, and it trains attention Unet over multiple epochs. And then the result here is we store the plotted metrics into graphs, loss, accuracy, and IOU. The other approach is a Rasa run server with action server that can also run on the Jetson TX2. And behind the scenes, we have, well, in upfront Unity, where the radiologist interacts with Rasa, saying, for instance, show me breast cancer segmentation report. That gets sent over to the Rasa server. Rasa asks which model we want to run. We say attention Unet, and then Rasa will go run that particular action through natural language understanding. And we can see the processing is happening, and we get back our qualitative results here. Original test image with the test mask, the predicted mask, the segmentation is shown to the radiologist. Next, what we'll look at is a pre-recording of our code walkthrough. So first, we'll look at the architecture diagram again, for quick reference. So we have the Unity part where the radiologist is at, Rasa server, action server, Python scripts. We have the route of running Python scripts to run our application. And we also have the route of running the integrated Rasa Unity application. So the user could start with train PY, gets the ultrasound, the train results to store the plotted metrics. We run prepare function, train function, as well as the evaluate function. So then we get back the training images and masks. We get back the trained attention Unet model, and then we pass that train model into our evaluate function. And then in this case, we're looking at the train attention Unet. We're getting back the model. Here's an example of attention Unet architecture. And then we train it over 25 epochs, validation split of 20%. Here's the case where we run the evaluate function, plot the qualitative, the metric results, loss, accuracy, IOU. And then here we deploy the model. That's the deploy script. So we get back deploy model, passing in test images and masks. In the deploy model, we load the image. We also call on display function. We plot the qualitative results. We get back the save file, and then we leverage that code in our Rasa infrastructure for Rasa's actions. We're using a lot of those helper functions. So here's the train lesion segmentation action. Radiologists will send that request through Unity, and then we'll send that save plotted metrics file to Unity to render it in the chat window. Here's the run lesion segmentation action. Again, similar, but it'll save the qualitative results into a file and then send that to Unity. And Unity will render that to the chat window for the user, the radiologist, to see. And thank you for your time.